He holds a PhD in computer systems engineering from Monash University, which was partly supported by the Endeavour Australia Asia Award. His research interest lies in the optimization for computer vision and machine learning, and its applications to intelligent satellites and space robotics. He has published more than 100 research articles on that subject, and he's won several awards for it, including a CVPR award from 2015. Tajun is also the director of machine learning for space at the Australia Institute for Machine Learning.
Thank you, Tolga and team, for organizing this wonderful workshop, and thanks for inviting me to speak as well. This feels like the second half of my quantum computing course currently. Everyone call me TJ, please do that. That's my initial. And, second half of the semester in the quantum computing course, I'll try to make things interesting, okay? So this is the outline. And acknowledgements go to my wonderful team who made this presentation possible. I forgot Xin-Fang's name down there, sorry. Okay, let's go to the beginning. Which one is the Earth? Do we need to take a poll here in this audience? All right, which one? Literally, I'm asking here. Number 1, number 2, number 3, or number 4? 2, 3. Is there a 4 at the back there? Anyway, no one knows the answer to this question in the mid-18th century. So we had to find out, right? But how would you find out? Well, if you think of Polaris as a point source that's infinitely far away, then you could try and measure your angular distance from the horizon, wherever you are, to Polaris, right? You can look at the sky, oh, there's Polaris. It's 45 degrees from the horizon. All right. Now, if the Earth were perfectly spherical or a perfect spheroid, then the angle that you measure Polaris would be exactly the angle of your latitude. All right. If it's an oblate spheroid, then the situation is different. You can measure Polaris at 45, but your latitude, this angle subtended by this red line and equator here would be less than 45. All right. So that provides a clue to find out. Okay, so mathematically, it looks like this. If you can obtain measurements of the arc length at several locations, arc length for 1 degree of 1 degree of difference in Polaris going up or going down, and then you check where your latitude is, and you can plot this curve, right? If the Earth was an oblate spheroid, you would see this curve, right, between the latitude and the arc length. If it were prolate, then it would look like that. Okay, if it's a perfect spheroid, what would the curve look like? A horizontal line, straight line, all right? So that's one way to find out. So someone was trying to find out in 1755. His name is Roger Bošković. He comes from present-day Croatia. So Bošković's data looks like that. This is at 1755, reprinted in a subsequent journal article. So we got 5 measurements from 5 different locations, different latitudes, and different arc lengths. The twice up there is an old measurement of distance. And I've converted that to this data here, okay? And I've also did the sine square instead of sine, so we have straight lines instead of sinusoid, okay? So he has these 5 measurements, and now he tries to find whether it's an oblate or prolate spheroid. So if it's oblate, then you would see an increasing linear curve like that. If it's prolate, the curve would be sloping the other way. Okay. The problem that Bošković faced was this was 50 years before least squares. He had more measurements than he had variables. Okay. There are only 2 variables, right, to define that line, but he has 5 measurements. He didn't know what to do. All right. This is 50 years before least squares. Jean-Marie Lejeune published least squares in 1805. Legend has it that Gauss invented least squares in 1795. He didn't publish it yet. Probably couldn't get past the reviewers. Didn't beat Sota. trying to make you all laugh here, right? Boscovich can already solve this by checking every pair. Why do we need least squares? But in hindsight, everyone credited Gauss with the invention of least squares because he communicated to his friends about his results first. So moral of the story, always push your work on archive. Okay, so Boscovich didn't know least squares. What do you think he did? He knew given every 2 points, he knew how to estimate the line. Guess what he did? Guess what he did? He checked every pair. Okay, there's only 5 points. He checked every pair of them. These are all 5 choose 2 pairs of line estimates. He said, these 2 estimates that go through Cape of Good Hope looks weird. Let's throw it away. These 2 ones that also pass through Cape of Good Hope, let's throw it away. In modern times, what do we call that data point, Cape of Good Hope? An outlier. Okay, that's what Boscovich did. And then he averaged the resulting lines. So this is the modern estimate, actually quite far away from the modern estimate, but good enough to establish that the Earth's shape is oblate. You've seen this algorithm before. It's called Rensek. Boscovich checked every single pair. Fischler and Bowles used a computer to go through the pair sequentially, using a classical computer. Can we check every pair in one go? Is the starting point of this discussion. Okay? So I don't need to motivate these slides to you. These are very, very influential computer vision problems. I'll slide this one in because that's where the funding comes from. You can do this in space as well on satellites, and the name, and then you can do post estimation, for example, by solving the P&P problem. So I think one of the things I learned from this workshop is to motivate quantum computing well in the computer vision community, we need to use the computer vision language. Michael has his Smeagol. The name of this satellite is Tango, all right? So we need to use things like this to bring the community along. Anyway, enough about bringing community along. So in computer vision, we solve the problem of maximum consensus or consensus maximization, all right? You would find the model that gives you the most number of inliers possible. Model being parameterized by vector X, you check all points, you find if all the points can fit inside a line with error epsilon. The downside of giving you my phone is that I can't keep track of time. Thanks. Okay, so epsilon here is vital to mention that it's an inlier threshold that's constant, that's given by the user. Right, we all know what this problem is. So, but to hammer it in, this is a 1D subspace example. It is kind of a running example. So I'll spend time to talk about this. You want to fit this line that goes through the origin. That's why it's called a 1D subspace instead of a line. And this particular candidate, for example, has a low consensus because the number of inliers in that epsilon band is small. This one has a high consensus because the number of inliers are big. Okay, so we want to find the highest possible consensus line. Okay, so that's the setup. What are the fundamental limitations? Every time I present this, someone says, Rensek already works. I agree, Rensek already works. But then every problem that we discussed in this meeting so far, maybe with the exception of Anand's, everything, there's already things that work. So no apology on that. So in Rensek theory, if you can check, or there is a technique to verify, actually you don't even generate all these minimal subsets. If you know what inlier rate is, if you know the dimensionality of your problem, you can probabilistically sample T samples, and you can sample T samples given by this equation here with some probability of gamma that you can determine. The key point here is that you can find at least one minimal subset that contains only inliers. So here's an adversarial case that shows that that doesn't work all the time. You have the data points here in blue. And the line that maximizes the consensus is actually this line here. And as you can see, it doesn't pass through any of the data points. You can check through all your minimal subsets. In this case, the minimal subset is size 1 because this is a 1D subspace. None of them will give you the maximum consensus set. And secondly, not all inlier subsets give you a good fit anyway. So the Rensack premise is actually wrong. This is now a line fitting problem where your line is allowed to go out of the origin. And these 2 points are inliers, and you fit your minimal subset, it gives you a bad estimate. So in practice, Rensack usually works, but when it doesn't work, you don't know why. You don't know it's because there are no good models to be found or because you were unlucky. So you have to run it again. Okay, more theoretically, we've established results surprisingly for the first time in computer vision that this problem is NP hard. It's W1 hard in the dimension, which implies that doesn't matter what you do, any algorithm that you come up with to solve this exactly will have D in the exponent of N. So it's always exponential. And it's also APX hard. That's even more pessimistic. There are no polynomial time approximation algorithms. Rensack is not an approximation algorithm by definition because it doesn't tell you how far you're away. There are no error bounds. Slightly positive result, you can show that it's fixed parameter tractable in a number of outliers and dimension, which we presented at CVPR 15. So you only scale exponentially with the number of outliers, but the number of outliers can be big in practice. So this is still not the solution. So here's sketching out the landscape. On the left-hand side, you have heuristic or randomized algorithms such as Rensack and variance. On the right-hand side, you have exact algorithms where from the theory, there can be no hope of any efficient algorithms. On the left, the algorithms are very fast, usually, but there are no guarantees. And the theory says you can never have any guarantees because it's APX hard. If you want to be fast, it will have to be, no guarantees. For Rensack type variance, there's also randomized behavior. On the right-hand side, you are condemned to be slow because that's classical computers cannot solve that, but you get optimality and you get deterministic behavior. What is in the middle here? It seems that we're only stuck with these two extremes. And more importantly, is there a role for quantum computing in this landscape? So that's sort of our second starting point, second motivation as well. I slid this slide in to very, very superficially show you the different types of quantum computing technology. You've heard presentations on quantum annealing earlier. That's on the left-hand side. The middle one is an analog quantum. I don't even know what that is. On the right-hand side, there's a universal quantum gate quantum computer. This slide was put up by IBM. Okay, so I'm not claiming any credit, certainly not claiming any veracity in these comments as well. They're probably right, but they're not this is not my slide. All I want to say is that the method presented in this talk is on the one on the right. So not quantum annealing, but quantum gate computing. So down here on generality, you can see that it says it's complete and known speed up. What I understand by complete is that a gate quantum computer, you can look at the theory. Any problem that you can solve efficiently, i.e. in polynomial time in a classical computer, will have a polynomial runtime on a quantum computer as well, okay? That's just a really superficial comment I make, but it will come back later during the results. Okay, so now the mathematical derivations before we get to the quantum computing bit. I'll try to make this as quick and as painless as possible. I will only summarize the main points that you really need to know. Okay, so we have to restrict somehow the set of problems that we look at, okay? And the restriction comes in the form of the type of residual function, the error function we use to decide inlier or outlier in our problem. Specifically, we look at error functions or residual functions that are quasi-convex. These are functions that are almost convex, but not actually convex, right? So how you define a quasi-convex function is that every alpha sub-level set of that function is a convex set. Okay, so on the left-hand side here, you have a quasi-convex function. It doesn't matter where you put this alpha, the part of the curve or the domain under the curve below alpha, this red line here is always connected. It's always a convex set in a higher dimension. This is not a quasi-convex function because here's an alpha where the domain is not connected, therefore not convex in higher dimension. The reason for imposing this, I will again remind you later when we get to that point. So here are examples of residuals that are quasi-convex. They happen a lot, not a lot. They happen in a few important problems in computer vision, such as multi-view triangulation or homography fitting. So no need to spend too much time on that. Just rest assured that there are problems in computer vision that satisfy these restrictions. Now that we are restricting to quasi-convex residuals, define the minimax problem. Minimax because you have a min and a max of a set of these quasi-convex residuals given a model X, okay? You want to find the X such that the maximum error is as small as possible. So for example, the blue curves here are a set of quasi-convex function. The max over this function, these functions will be that red line here. And what you can show that it doesn't matter where you put the alpha, the maximum of the quasi-convex functions are still quasi-convex because that red line here is always contiguous in the 1D case or convex in the higher dimensional case. The crux of this is if your residuals are quasi-convex, then you can solve this minimax problem in polynomial time, all right? You guarantee that you can solve this in polynomial time. It's efficient, therefore, in theoretical speak, and that will have implications later when we move to the quantum. Here are sample problems that you can solve, sample algorithms that you can solve this. So, give you more intuition, maybe forget about the circle one, because we started with line fitting. Look at these bunch of points on the line with some outliers. The minimax problem is to find the band that is as tight as possible that covers all the points, okay? So given a bunch of points, push the boundary lines top and bottom, make them as tight as possible so that you cover all the points. When I say minimax problem next, or when I say function G next, that's the picture that you should have in your mind. So if it's quasi-convex, then if residuals are quasi-convex, then the minimax problem G is also monotonic, meaning that if you have data points that are subsets of each other, G of B is always smaller than G of, is never bigger than G of C because B is a subset of C. Okay, so again, to motivate that, if I throw more points into the set of blue points here, the minimum width band cannot reduce. It can only stay the same or grow bigger. Okay, so that's what monotonicity means. So coming back to our target problem, which is to find the band of size epsilon that has most of the points possible. That's our target problem, right? If someone gives you a bunch of points and say, that's the solution to your maximum consensus problem, how do you check? You check by solving the minimax problem on that bunch of points, push down as much as possible until you can't push down anymore, and check if the width of that resulting line or resulting band is less than or greater than epsilon. Less than or equal to epsilon. If it's less than or equal to epsilon, then the subset that you solve the minimax problem on is a consensus set. Not necessarily the maximum one yet, we'll get there. Okay, so then this allows us to reformulate our target problem as this. If you have I being the set of all subsets of your data, you can re-express the consensus maximization problem as find a subset that has the most number of inliers. You all know this already, all right? This is just using the minimax language to express it. Monotone Boolean functions and influence. So another reformulation, please bear with me because this is needed to squeeze this into the form that we run on the quantum computer. If you have n data points, we define a vector Z that contains nothing but binary elements, binary numbers, and these binary numbers basically select the subset of points of your data. Okay, so define a set C Z as just the index of the Z's that are 1. Okay, that's it. And then we define a feasibility test F over this binary vector Z. The feasibility test returns 2 numbers, 0 or 1 only. It returns 0 if vector Z includes a set of points that are feasible, that is a consensus set. If it's not a consensus set, if Z doesn't represent a consensus set, then the feasible value is 1. So we can say that the function f is monotonic or monotone, because if I give you a Z and then I OR that Z with another Z, the feasibility of Z cannot improve. It can only become infeasible. It cannot become feasible by adding points. All right. When you make it as tight as possible and then you throw more points, you can never make it tighter. You can only stay the same or grow bigger. That's what this is saying. Okay. So f is a function that's monotonic. It's a binary function that's monotonic. This is the key feature that we use in our work, given that setup. Let EI be just a vector of all zeros except 1 at the ith position. The influence point P, alpha I, is the probability of, if you pick any Z, sorry, the influence of a point PI, the ith point, PI, alpha I, that's the influence, is the probability of, given any random Z, if you take the point, the ith point in or out of that Z, so in the case where Z originally contains the ith point, take it out. That's what the XOR does. If the point doesn't contain I, add it in. That's what the XOR does as well. And then you check before and after adding or deleting EI, does the feasibility of Z changes? That's what this is saying. And then you ask, what is the probability of this changing, of the feasibility of F changing? What is the probability of F changing value given you add or delete the ith point? In other words, how much influence, how much weight the ith point has on this feasibility question? Okay, so analytically, to evaluate this probability, that's what you do, right? You loop over all possible 2 to the n values of Z. It's a binary vector of with n binary variables. All right. So the number of combination is 2 to the n. You loop over all of them and you count the number of them that causes this flip in the feasibility. This is what it looks like. This is a bunch of points that I generated synthetically. Well, the student Xinfang generated synthetically. Therefore, she knows that the red are the outliers, the blue are the inliers. Let's compute the influence of every point exactly following this equation here. And this is what we get, right? We compute the influence, we sort the influence value, we normalize the influence first, we sort from large to small, and you see a distinct gap between the outliers and inliers. Will this work on computer vision data? Even better, it works in computer vision data. So this is a triangulation problem. Remember I said that triangulation has a pseudo-convex residual. Therefore, the f function needs you to solve the g function, the minimax. The minimax is always polynomial time solvable because the residual is quasi-convex. So you can also see this distinct gap between inliers and outliers. So the outliers here are wrongly localized feature locations. The color coded here on the left-hand side because it's manually labeled. And you can see a distinct gap between inliers and outliers. And for correspondence problems across 2 views as well, I think we're estimating homographies. Again, you see that the gap is even bigger. Okay, so this tells you that, hey, this is actually a good measure of outlierness. The trick is, how do you compute it? The strict definition of it says you have to check all 2 to the n possible values of Z. How do you use your computer to do it? Any ideas? That's what we did, brute force. With 20 points, 8 dimensions, you can brute force, no problems. If you have more points, what do? You go back to Mr. Fischler and Bowles' algorithm again. You do random sampling. Okay, so the classical algorithm literally is selecting subsets, and then you collect statistics over that subset, and you now have an approximate value alpha hat over the true influence, which you have no hope of computing because it's exponential. Small problems you can, big problems you cannot. And then you collect that statistics over a subset Z instead of the proper set Z over with 2 to the n possibilities. And that's literally the classical algorithm. And then you average the results over m of these trials. Every time you pick a k tuple from the data set, it's exactly like Ransack. You check and then go for every model that for every Z you return. So every subset that you sample, you go through every point, add that point in or remove that point for Z, see if that changes the F. You collect that statistics, and then you average that over the number of samples or tuples that you've chosen. All right. The total number of F evaluations is n times n. M samples, m sampling of k tuples, and n data points. You can speed it up somehow. You can speed this out by recognizing that for quasi-convex residuals, you don't actually have to fit k tuples of any size. You just need to fit the combinatorial dimension of the problem, which is d+1. So 3 points in the case of line fitting are sufficient. So one innovation that you can do is to sample only 3 points. So that's a detail that we don't have to go through today. Now, what's nice about this realization is also now remember this spectrum here. On the left are heuristic algorithms. On the right are exact algorithms. We're trying to find a role for quantum computing. What we've discovered in the process is actually there's another class of algorithms we haven't considered, algorithms with probabilistic guarantees. The APX hardness says you can't have hard bounds on the result, but it doesn't preclude probabilistic guarantees. And by using this influence way of looking at things, you can prove a probabilistic bound on your solution. You know that with some probability delta, which you can control, you just need to control how many times you sample, your value of the true influence and your estimated influence is probabilistically bounded by that value there. And we didn't believe it at first, but we tried it out experimentally, and hey, it actually does work, and you don't need to try a lot of iterations. For this small number of lines here, with just a few hundred iterations, you can already have very good probabilistic bounds. And the more you sample, of course, the tighter that probabilistic bound becomes. And it works on the real data as well, so I won't go through this. All right, finally, the quantum algorithm. I have at least 10 minutes, I think. We started off with the premise, can we check all the subsets simultaneously in one go? And then I told you that's actually a bad thing to do because none of the subsets will give you the right results. None of the subsets will give you, there are adversarial cases where none of the subsets will give you the result you're looking for. And then we switched to using influence instead, computing the influence of every single point instead of estimating the model. So the circuit we ended up using is called the Bernstein-Wasserstein circuit, or BV circuit. It looks like that. It's a very, very standard quantum circuit in any quantum textbook. So we did not invent this at all. The key thing is that the function, Boolean function f, is implemented implemented in this block here, and the data points also must be implemented in this block. Bear with me, that's a leap of faith that's doable at all, but bear with me. If we can implement our function f and encode our data in this quantum transformation f, what can we do? We can rest assured that because f that we're looking at is classically polynomial time solvable, there has to be, the math says there has to be a quantum implementation that also uses only a polynomial number of gates, okay? So therefore it will have, not that it should have, it will have an efficient quantum implementation. Is a spoiler, we just don't know what it looks like, but there is one. So if there is one, if we know how to implement f, what can we do? We initialize a circuit, BV circuit with n+1 qubits. The top n qubits, which encodes the selection, that we're interested in with the 0 state, and then the n+1 qubit with the 1 state, and then phi1, the composed quantum state with the tensor product that Michael introduced earlier is that. And then you pass it through, you put it through uniform superposition, which means that you also put it through a composition of n+1 Hadamard gates. So now the phi2 is nothing but a uniformly superposed quantum state. Now you pass it through the function f. Okay, so I'm not going to go through the detail because it's actually not that important. Everything that I've said here are very, very standard quantum operations. Honestly, if you ask me now, how do we get here from here? I have forgotten because it's so standard that I didn't bother to memorize it. So what we want to get at is after we pass it through function f, we pass it through the n+1 composed Hadamard gates again, and you can show that in the top n qubits, you have exactly the influence values that you're looking for. In one quantum step, in one quantum transformation, you check through all the combinations to the n, and you get all the n influences that you're looking for. So that sounds good, right? But it isn't, because there's always a catch. Yes, the state that pops out of the quantum circuit contains the values you're looking for, but you need to measure them before you get anything sensible. So once you measure them, the phi4 state collapses, and that information is lost. Okay, you can get empirical samples of it, and that's what you have to do. That's what the only thing nature allows you to do. So then what do? We run the circuit again. Okay, again, we're having to do sampling. We run the circuit m times. Every time the circuit is run, we sample the alphas. And by sampling, meaning we're just saying for the ith point, is it an outlier or an inlier? Sample from the, measure the qubit corresponding to that point, see if you get 1 or 0. If it's 1, it's an outlier. If it's 0, it's an inlier. Then over m times, calculate the statistics of that. And then you can use the same analysis with the Hofding inequality to show that, okay, you can also place the same probabilistic bounds on it. So the speed up we get is, remember that in the classical case, we need to evaluate f n times m times, n times m times. In the quantum approximation case, we only run this for m times. The inner n loop is no need. Okay, you can just directly sample. And we showed that this approximation algorithm does work as well. This only is simulated because the trick of putting the f function in the block is work in progress. So as I said, the catch is how do you implement f? We know one must exist, all right? Because it's a polynomial time in classical. Work in progress, we're working on this. Yeah, we're hopeful that something can be done. I'd also like to advertise another line of work towards this robust fitting problem that uses quantum annealing. basically transforming to the problem to a hypergraph vertex cover problem, which has a convenient Cubo implementation, and therefore we can chuck it into the quantum annealer directly. So I'm not going to go through details of this. Comparisons between CPU and QPU, details are in the paper, or come and talk to me. And here are some references for our line of work here. I'd like to end this talk by quoting Peter Shor. Shor is, of course, the originator of the factorization algorithm, the one with the exponential speed up. All right. So he wrote a survey paper or communication paper, why haven't more quantum algorithms be found? And he listed a few reasons. Partly it's because the quantum approach is so different that algorithm designers are finding it hard to dream up or come up with new algorithms. There are other reasons that he hypothesized in the paper. But in the last paragraph, he says, one research area that might be worth exploring is to try to find faster quantum algorithms for problems that already known to be classically solvable in polynomial time. So I think it was Michael who mentioned the big factor at the front. So this is Peter Shor saying, maybe we should look at that factor instead of trying to justify quantum always by trying to find that super polynomial speed up. And I think that's the approach that we need to take in computer vision as well, with GPU GPU solutions being so successful. It's hard to beat, and we need to be more, I guess, realistic with what we can achieve and what we can convince the community with. And thank you very much.
Thank you a lot for that really engaging talk. And we have time for a few questions. And I would actually start with one. When you measure the relevance of each of the points, do you need to measure them separately due to entanglement, or can you measure all of the points at once?
I think you measure them separately. I could be wrong on that.
Okay.
I think you measure them separately.
Thank you.
Yes.
First of all, thanks a lot for the very interesting and nice talk.
Thank you.
I'm wondering, do you have a proof that the point of, say, least influence is actually an inlier in the best solution to your original problem?
The original problem, no. Mm-hmm. So the problem that we end up solving, that we end up converting to so that we can push in the quantum solution, is already different from the original problem. Okay.
Do you know a counterexample or adversarial case?
I have no counterexample yet, but my colleagues have done an analysis on the ideal single structure case, where you know the distribution of inliers, you know the distribution of outliers, and it's provable that the influence is a measure of outliers. So one positive case, I think, there are probably an infinite number of adversarial cases.
Thanks.
Thanks.
Any other questions? Maybe I can ask one.
Yep.
So regarding the paper on robust fitting with quantum annealing, so I think you've compared the CPU against the QPU. I would wonder, on the high level, how do the gate-based version of robust fitting and the adiabatic version, so AQC version of robust fitting, compare on a high level?
On a high level, that we haven't done the comparison because we haven't figured out exactly how to put F in the gate model yet.
I see. Mm-hmm.
So that's work in progress.
Mm-hmm.
Once we get the results, we will email you. Current results tells me that the gate model will also suffer from noise because of decoherence or whatever, and which is not different from the quantum annealing.
Okay, thank you. If there are no further questions, let's thank the speaker once more.